Hey guys, welcome back to the next session of Insertion Sort. In this session, we are going to look at how the code of insertion sort might look like, and then we are going to do a thorough analysis of the insertion sort algorithm. So when coding, there are million ways one can code a solution, and I am going to code based on the insertion sort example I did in the previous session. If you haven't looked at that example, I recommend that you go through that example so that you have a fairly good understanding of how insertion sort works in theory, and that is going to help you understanding this code a little better. So let's see. I have a insertion sort class in app.java. I am passing it a array, creates a insertion sort object and passes the array to the object. After that, I call the sort function on the insertion sort. And inside the insertion sort, I have an array which is initialized in the constructor, which is passed from app.java. And then in the sort function, we are going to quickly do the sorting of the array. So first, let's say I am going to write the code in a much simpler manner. There are more ways where the code can be a little short, but I am going to write it more elaborate so that everyone is able to understand it. So array dot length, I'm going to save the length of the array. After that, I am going to do a outer for loop which goes from 0 to n minus 1, and right, and this is exactly how I did in my previous example on insertion sort. After that, I'm going to save the value at index I in k, and I am going to do j, which is I minus 1. So that's how I demonstrated in the example that j will always be initialized with a value I minus 1. So j starts from one index less compared to I minus compared to I. Let's do a while loop where j should be greater than or equal to 0. As soon as j goes below 0, or so j should be greater than 0 and value at j should be greater than the value of k. Then we keep on iterating the inner loop. So value at j greater than k. If this happens, we are going to shift the value on to the right. This means the value on the right is going to be written the value on the right is going to be written from the value on the left. I will again repeat that. If you haven't watched my previous video on the insertion sort example, please do that. Right? And I'm going to increment j by 1. Once the loop is done, I am going to write the value at index j plus 1 with the value from k. And this is the insertion sort example. Now, let's run it. And I'm going to put a breakpoint here. Okay. And once I call this, let's see the value of array. See, it's already sorted 2, 3, 4, 6, 7, 8, 9. So our sorting code looks to be working fine. Okay. Now, let's see how much time each code line is running. So this line runs for a constant time. This line runs how many times? Let's say n times. So we will say this is running n times a constant, right? This line runs one less. So I will say a constant n minus 1, and this also runs the same number of times, but maybe a different constant, because every calculation is different, so they have different constants, right? Because this line number 18, is not going to take the same number of processor cycles as line number 19. So we are going to have different constants for each line, unless both the lines of code are exactly same. Okay. Now let's come to this in a while, how much this is going to run. So maybe if this is some C4, C5, C6, then this is going to be C7 into how much? N minus 1 times, right? Okay, let's come here. Now this is a little tricky. Why? Because this is another while loop which is going to run n minus 1 times, but we are going to sum it, right? Because for every I, this is going to run n minus 1 times and not only once, right? So this will be C4 and sum from how much? I would say J is this. So this is actually running n minus 1 time. This is running sum n minus 2 because the inner code is going to run one less. And so this is a very high level analysis of what line is going to run how many times. Okay. Now let's do a little more detailed analysis of this code and comes up with the final time complexity of this code. Okay, so let's look at a more detailed analysis of the source code for insertion sorting. So I have copied the code which we did. Right? Okay. So I think lines this, and this are more clear, right? I will explain a little more on these. So because these lines are going to repeat multiple times for every value of I, we are going to do a summation, which means this will be from 0 to, for some t, 0 to n minus 1, right? And let's say I'm going to take it some of t, right? This will be t is equal to 0, n minus 2 t, and this will be summation of t is equal to 0, n minus 2 s t. Okay, so this is a natural number series which is n plus 1 upon 2, but because n is n minus 1, so we get n upon 2, right? Here n is n minus 2, so we are going to get n minus 2, and this one will be n minus 1, n minus 2 upon 2. Okay, so if we sum the whole thing, we are going to get C1n plus C2 n minus 1 plus C3 n minus 2 plus n plus 1 upon 2 plus n, no, sorry, mistake. This will be n minus 1 upon 2 plus n minus 1 n minus 2 upon 2 plus n minus 1 n minus 2 upon 2 plus C7 n minus 1. Okay, I forgot the constants C4, C5 and C6, right? Okay, so if we see what will be the solution for this, from here to here, these are linear time and this is linear time, right? Linear. And these are taking approximately n square time, right? So if we discard the lower order terms, we are going to get n square, right? Which is our worst time complexity as well as our average time complexity. Why average is the same? Because this loop either will run for the whole n minus 1 or this is going to run partially. Even if it is running partially, these sums are still going to take n square time, right? Okay. But when we talk about the best case, these are not going to run, which means if the array is already sorted, this whole while loop is not going to run, and these all time are going to take a constant time, right? So what we are left with is this and this. So this means our Tn will look like C1n plus C2 n minus 1 plus C3 n minus 2 plus O1 plus O1 plus O1 plus C7 and minus 1. So if you see, the square terms are gone, and what is left is only the linear terms, and this will turn out to be n. So the best case is n. This means insertion sort takes n square average will be n square and the best will be, and this finishes our formal analysis of the insertion sort algorithm. I hope this session was somewhat knowledgeable and gave you a good insight into how insertion sort works and how its time complexity is calculated. With this lecture, I'm going to conclude insertion sort, and we are going to start with our next sorting algorithm, which is called selection sort. So I'm going to end this session here, and I'm going to thank you for watching the video.